Ladies and gentlemen, good day. This is Jeans from AGHAMALAYAN, and today we're going to talk about calorimetry. But first, let's discuss first about the change of state. So, a substance may absorb heat without an increase in temperature by changing from one physical state or phase to another, as from a solid to a liquid, which can be done through melting, from a solid to a vapor, that is sublimation, from a liquid to a vapor through a to the process called boiling, and finally from one solid form to another, and that is what we usually call the crystalline transition. Now, let's define the meaning of latent heat. So I'm going to activate my yes, this latent heat over here. So latent heat is the name given to that amount of heat which changes the state of a body without changing its temperature. So let's first talk about the latent heat of fusion. So as we can see, we have the formula mass times the LF, okay, or the heat of fusion. So it is the amount of heat, this one, it is the amount of heat that must be added to a unit quantity. It can be 1 kilogram or 1 pound of a substance at its melting point to change it from solid to liquid. And for the latent heat of vaporization, it is the amount of heat that must be added to a unit quantity or 1 kilogram or 1 pound of a substance at its boiling point to change it from liquid to gas. So there are various heat of fusion and heat of vaporization constants for a variety of substances. For example, for water, we have the approximately 80 uh, uh, calories per kilogram for the heat of fusion of water, and for the heat of vaporization, we have approximately 540 calories per kilogram. So let's talk about specific heat. It has the formula C equals Q over M times delta T. So specific heat of a substance is the ratio of the amount of heat required to change its temperature to cause the same temperature change in the same mass of water. The symbol for specific heat is C, okay, sometimes S. Its SI unit is expressed as joule. Okay, I'm just going to write it down. So I'm just going to first activate the pen mode. This one here. So the units used for the specific heat are the following: joule per kilogram times degrees Celsius, including its other equivalent units such as this one. So K cal over kg, kilogram, times degrees Celsius, and the butane over pound times degrees Fahrenheit. So take note that water is said to have the highest specific heat capacity, but ice and steam, which are the changes in phase of water, have lower specific heat than water. So what is that? The specific heat of water, so I'm just going to write C sub water is equal to approximately 4185 joules per kilogram times degrees Celsius. Okay, and then for ice, okay, I'm just going to write it somewhere over here. For ice, so ice, it is equal to 2090 joules over kilogram times degrees Celsius. So as you can see, for the ice and of course the steam, They have lower specific heat than water. Alright, so this is our first problem. So we are asked to calculate the amount of heat required to transform 2 kilograms of ice at 0 degrees Celsius to water at the same temperature. So we're going to list the given and the required. So what are our given values? So given. So we are given the mass, which is 2 kilograms, and the heat of fusion, the L sub F, that is, of course, it's not given in this problem, but let's write here the heat of fusion of water. So it's 79.7 calories per gram. What is required of us? We are required to calculate the heat. Okay, that is Q. So the solution for this problem is the following. So I'm just going to change the color so it will be more attractive. Okay, and then here. So we're just going to use the formula that we had seen in the first slide, and that is mass times the heat of fusion. Next, we're going to substitute the values. That is 2 kilograms times 79.7 calories per gram. Now, we cannot just cancel kilograms here and grams there. So, we need to first convert this into kilograms, right? And then, our final answer, if you have already applied dimensional analysis, that our final answer should be 159,400 calories. Okay, so this will be our answer for this problem. Okay, next we're going to solve this problem concerning specific heat capacity. So what is given to us in this problem? So we're just going to first list down the given and the required. So what is given to this problem? So the given here is the mass, of course, that is 1 kilogram. The heat, what amount of heat is applied? 10 kilocalories. And then lastly, the delta T. So we have the initial temperature and the final temperature. So this is the final temperature, this is the initial temperature. So we're just going to write here the final temperature minus the initial temperature, and that will be equal to 24 degrees Celsius. So what is required to us? We're going to find simply the specific heat, which is C or S. So here's the solution to our problem. So I'm just going to change first the ink color. Let's make this light blue. Alright, so the formula for C is given by heat over mass times delta T. Now we have here the Q. We're just going to substitute the values. We have 10 kilocalories, and then here we have 1 kilogram times 24 degrees Celsius. And then finally, we already have our answer. Our answer is 0.42 kilocalories over kg times degrees Celsius. Okay, so let's solve this next problem concerning calorimetry. So we're asked this problem, so let's read it. 5 kilograms of water at 40 degrees Celsius is poured on a large block of ice at 0 degrees Celsius. How much ice melts? So in here we're going to list the given and the required. So in here we're going to write the given. Okay, so what are given to this problem? The mass of water, which is 5 kilograms, the delta T, which is the final temperature minus the initial temperature. So in here, uh, the final temperature will be the 40 degrees Celsius, and then the initial temperature will be the 0 degrees Celsius, and then we'll have delta T will be equal to 40 degrees Celsius. The heat of fusion, of course, it will be equal to 79.7 kilocalories over kilograms. Okay, and then the specific heat of water is 1 kilocalories over kilograms times degrees Celsius. Now what we're required to look for, so I'm just going to write here the subscript H2O. What we're required to look for is the mass of the ice. So I'm just going to write a question mark over there. So we're just going to change the color for this problem to for the solution. So solution. So in here we're going to use the popular Q loss is equal to Q gain. So the technique here is that the system that has the higher temperature, it will be the Q loss, and then the system that has lower temperature will be the Q gain. So that's the technique that I usually use when solving calorimetry problems. So our Q loss will be the water, since it has high temperature. So M water times C H2O, so I'm just going to write here H2O times delta T, okay, equals the Q gain, that is the heat gained by ice. So it will be mass of ice times the heat of fusion times the, oh, that's it. And then in here we're just going to substitute the values. So MH2O is equal to 5 kilograms, CH2 is 1, delta T is 4T. But I would like to isolate the mass of ice first. So it will be MH2O CH2O delta T, and then putting the heat of fusion in the denominator, LF. Now we're going to have MH2O, so that's 5 times 1 times 4T over LF, that is 79.7. So computing all of that in our calculator, we will have 5 times 40 divided by 79.7. We will have 2.5094 kilograms. So 2.5094 kilograms. So that's it for this problem.